All right, let's get started here. Welcome back to week 10. Dun dun. Okay, so we're gonna just recap a little bit about what we did last week. I'll talk about that for a little while, and then we'll move on to some other topics today, and we will set ourselves up for about a 3-week module on just regression coming up. Okay, so today is kind of like the setup to make the transition from what we did in the previous weeks to what we're going to be doing from next week onwards. Ali? All right, great. Okay, so let's get started. So what did we be talking about last week? So last week we did some, we finished talking about hypothesis testing, and we looked at ANOVA a little bit, bootstrapping it, some of the ins and outs of it, at factorial design. All right. I just want to start by just showing you some of the visualizations that students often use in their assignments. So this is from not the last assignment necessarily, but from one of the previous assignments. Just want to give people a glimpse of some of the types of visualizations people are using. So people are using histograms, they're using box plots and strip charts and density plots and colorful density plots. All right, so we're getting a lot of different types of visualization, which is great. You're not limited to one thing or one style, but I hope that also as you're doing your peer reviews, you're kind of getting a sense of the different styles that people are using, so you're getting some ideas from that. Okay, all right. So last week's assignment was about this experiment on emotion and color, and it's a real study. It wasn't something fictitious. It's an actual study that was published in a journal, and I'll talk a little bit about that today. Okay, so the study was essentially about what was the study about? What's that? I hear somebody mumbling something. Anybody? Accuracy of... Oh, see, one person is brave and other people get brave. Okay, good. Of accuracy of color perceptions. Okay. And what were they manipulating in this experiments? Something to do with emotion. Emotion condition. So they got people to look at, some people to look at a fairly neutral viewing, like a what was it? A screensaver or something like that. One group saw like a boring screensaver, and the other group saw a very emotionally charged video, the death scene from Lion King, considered to be one of the more emotional bits of viewing, especially for children as they're growing up these days. Okay, and they want to see if that affects how people perceive color, is if emotion actually alters their color perceptions. Kind of an interesting study. It's a psychological study. Okay, this is so I wanted to visualize that as well. So let me just kind of go and have a look at some of the things that I did to play with it. So load this up. Let's see. I wanted to kind of get a look at these two conditions and how people's accuracy varies under these two conditions, neutral and what's the other one? It's experiment. What was it? Sadness? Okay, yeah. So experiment dollar emotion condition, right? So and it appeared to be sadness and neutral. All right. Okay. So I wanted to kind of get a visualization of this, and I wanted to produce something that looks like this, just like two sets of box plots, one for the blue-yellow perception, one for red-green perception, and I wanted to do it for neutral and sad for both. Okay. However, I want to view them at the same time. I mean, I could do this. I could do this box plot, and then this box plot, and then I could quickly jump back and forth and try to see, hey, does that change? Does that change? But it would be nice to also kind of just to be able to see them together at the same time. And there's a little trick, if you will, in R that allows you to do multiple plots in the same window without changing your plotting code at all, actually. And the way you can do that is this little command called par, and that allows you to define how to separate your plots on the same graphical outputs. Okay. So for example, this command par with parameter mf row set to C12 basically says I would like to have one row of visualizations with two columns, with two separate columns. So let's see what that does. So I'm going to call that command. It says one row with two columns. Nothing has changed. Let me do my first box plot again. This time when I do the box plot, you'll notice, boop, it appears on the left because there's two columns that I've defined for the graphical outputs. Okay, and when I do the second box plot, boom, it's on the right. All right, I'm doing my own sound effects. You won't get those at home. All right, okay. And that's one way that I want to let you know that you can actually do multiple plots on the same plotting window. Okay, just with this par function and the mf row parameter. All right, so that's kind of handy. I do have to tell you one thing. After you're done with your plotting, please, 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 for your own sanity, set this function back to 1, which means just one plot at a time. If you don't set it back, then for the remainder of your session, everything you'll plot will alternate between the left column and the right column. It'll drive you nuts, okay? So if you use the par command with the mf row, then please set it back to 1. All right, so then you get something that looks like this. Yeah, question?
I have used the par function.
Oh, cool.
But my problem is that, for example, when I reset it to 1, and I want to do like the line plots, like you add lines in the same graph, it doesn't anymore.
Huh?
So
really?
Maybe it's something with
Could you do us a favor? Could you share the code that you're having problem with? And
it was like in the first
okay.
But it was like in the first assignment.
All right.
So I had to literally close the project
And reopen the project.
Open it again, so it can reboot as it was.
System. Okay, so if you run into this again, please share the code with us, because I have not run across that after doing par mf row 1. So, but if you do, please let me know, and I will. We will try to figure out what's going on. Maybe there's a better command to reset the graphics. There's a couple of other commands, so we may have to play around. Maybe there's a more powerful command that you need for your needs.
It comes back to 1, like.
Right.
What you want to put, well, at least in my code, when you want to put all the
Add
lines
more
together,
lines. Oh.
They graph another thing and graph
I
another
see.
thing,
Got it.
graph
Got it. I understand now. I hadn't considered that use case, so I'll try to look into that. Thank you. Thank you. Okay, I get it now. Cool. Not cool, actually, but it's all right. Thank you. All right, great. So this is our visualization, and do we see some difference? Well, it's a little difficult to really appreciate much difference, because first of all, we're going to run like a couple of t-tests on this. Did I ask you to run an ANOVA as well on this? I did. Okay, great. So we're going to run a couple of t-tests on this. But t-tests and ANOVA, what are they actually comparing? What are they testing? What two things are they comparing? What's that? The means, right? And guess what's not on this visualization? The means. They're not here. So we're not really looking at the means at all. So that's a bit of an issue. How could we try to resolve it? There's a few ways. Let's take a look at one possible way, okay? And this is not necessarily the best way, it's just one way to do it, okay? So what I did instead is I tried to make a visualization more like this, and I'll kind of show you the rough idea of how that goes. I don't want to get stuck in the code for too long, but so essentially what I'm doing is I'm going to compute the means and standard errors of the two groups. I mean of the two perceptions, red, what was it, blue, yellow, red, green. So I'm computing their means and their standard errors, because after all, that's exactly what the t-test is going to use to do its testing, right? And then back to parmf row. Okay, so here is one set for the blue yellow, and all I'm showing you here, these are bar plots now, not histograms. These are bar plots. So I'm showing you a bar that's showing you up to the level of its mean. Okay, this is telling the mean of one and the mean of the neutral and the sadness. Now what I also want to see is how does that mean deviate, like potentially across samples. The standard error tells us that to a certain degree. We know the mean should have a kind of sort of a normal distribution with standard deviation, the standard error. Okay, so I've also computed the standard error, and now I've written a little function for myself. Let me show you what that function does in a second. So that function draws little error bars for me. Yay! So it's drawing little error bars for me to show me what is the, as you can see here, 95% confidence interval of the mean. All right. So this is the mean. This bar plot is the mean. It's a little unusual to view a mean as a bar plot, but anyway. But you can see the 95% confidence interval of that mean here. Okay. So in this blue-yellow case, whoa, yes, it does appear that, you know, the 95% confidence interval of one of the means could appear to be a little bit different than a 95% confidence interval of the other mean. It could be the case. Okay. Let's do the red-green one now. There's the red-green one. There's this error bars. All right. And this one looks, okay, now these two confidence intervals appear to overlap considerably more. All right. So the sadness condition for red-green seems to overlap largely with the neutral condition. Largely. Almost entirely. Okay. So I don't expect a big difference in the red-green, but whether we can statistically detect a difference in the blue-yellow is a question. Okay. And all right, what else can we do? Oh, we can draw an interaction plot. Bang, that's our interaction plot, and that shows us the neutral and sad, a line connecting neutral and sad means for blue-yellow, which is this dashed line, and for red-green, which is this solid line. Okay. At this point, it does appear that, hey, look, these are different, right? If you are looking at blue-yellow perception, it does appear that you feel not only sadder than if you were looking at red-green. That's not the key point. The key point is that, like for example, when you look at the neutral condition, the difference is not all that much between blue-yellow and red-green, but the difference is quite a lot for blue-yellow and red-green for the sad condition. Okay, this is what we call an interaction. It's not that it's not important that the for interaction, what we're not looking for is whether this dashed line is below or above the solid line. What we're looking at is that their slopes are actually different. Okay, this tells us that the difference between neutral and sad is actually different for different color perceptions. All right, so this is kind of an interesting way of looking at what's going on here. And then we did, so that's kind of to give you an idea. Now, in case you're wondering how I did this code to show this error bars, those error bars are actually drawn with the arrow function. The same function I used. Did I use that before? No, I did not. I've not used arrows before. It's very similar to the segments command I used in the previous weeks to draw line segments. The difference is with arrows, with the command called arrows, after it's drawn the line segment, you can draw something at the beginning and the end of the line. In this case, this code equals 3 tells it I want to draw just a flat head on the beginning and the end of the line. All right. So that's an arrow function. Otherwise, it looks very similar. You give it the starting x and the starting y, the ending x and the ending y. Okay. This, excuse me, and this angle, I suppose, probably tells me how the angle of the arrowhead. So I think the 90% is saying make that arrowhead. You should look like a sharp arrow, but make it like zoop 90%, 90 degrees. Okay, so that and the code 3 together, I believe, is producing this flat shape, allowing me to draw error bars. Okay, all right, cool. So there appears to be, and then if we run, before we run tests, I do encourage you all to play around with visualizations and try to make your own custom visualizations. Sometimes it'll be really weird and not worth pursuing, but sometimes you'll stumble across a visualization that is better than just using, I don't know, density plot, box plot, bar plot. Like, rather than just using like the standard ones, you might be able to come up with your own custom visualization that is more meaningful to your particular context. Okay, so don't be limited to what you have. Try to play around with things. I will mention that like in some of the research projects I've done in my lab with like students, particularly with my PhD students, we often find that a custom visualization expresses so much more than just using a standard visualization. It's because we know the problem better than anybody else, and we can visualize it the way to highlight the things we want to highlight. Okay. Little segue, just a little side note. I gave an optional reading, I think, on Canvas. Did I? This was from The Economist, and it was called Mistakes. We've drawn a few. Did I post this on Canvas? Yes or no? I did. Right? Okay. Did I? Yes. I mean, I'm not asking you if you read it. Don't panic. I'm asking you, did I post this on Canvas? Yes? Okay. All right. Read it. It's from The Economist, and The Economist is a well-reputed journalistic outlet. And they read a really nice article about all the bad data visualizations they used to use in the past and how they have improved and like how they've made it more meaningful. And they give several really interesting examples. Do I have the so let me Canvas. Let me just try to find that article really quickly. What year is it? Okay. And mistakes, we've drawn a few. All right. Do take a look at this in your spare time. All right. And they give some really nice examples of things that they did in the past which created strange or misleading figures. So for example, they have this example here where they had these two trend lines. However, these two trend lines are actually on different scales, but originally when they published this figure, they chose scales that made it look like these two are like following exactly one another. And they said, wow, isn't it interesting? These two things are correlated. Later on, they realized, if you change the scales, they would not look like that at all. And they had arbitrarily picked scales to make it look heavily correlated, okay? And they give some other nice examples. Here they were using a kind of plot that like weaves between every single point in an opinion poll. But then they realized if we just do a scatter plot and just kind of draw a trend through them, it doesn't look exactly like what the figure on the left shows. So they kind of say we could have done it better. All right, and so on and so forth. So if you're interested in data visualizations, absolutely do take a look to kind of see why they think the ones on the left are the ones they published originally are not as good as what they think they can do today. Okay. An interesting little point that they make, and they just copied this paragraph out of it. Why were they making worse visualizations before? And one interesting thing they said is before they were using some well-known visualization tools, applications, which had some default ways of showing things. So they were just kind of going with the default visualizations of the tools they were using. And later they switched to R. And their whole data analytics team and visualization team switched to R, and they realized they could make much more sophisticated and custom visualizations and not stick with like the defaults of just some statistical application. All right. So they make a really good case for learning better tools and being able to programmatically create visualizations. and not just kind of assume that the way a standard application does it is the best way to do it. Okay. So anyway, that's a little segue to tell you, play around with custom visualizations, make your own things. Okay, because now you have the power to do that. All right. Cool. Okay, moving on. So we can do the t-test of these conditions. So one thing I asked you to do was 2 independent t-tests, right? And one t-test was on the blue-yellow accuracy and in the sadness versus the neutral case. All right? And we do find that, as some of the visualizations suggested, there is just a very narrow, it is just narrowly significant at the 95% confidence interval. Excuse me, at 5% significance. At 5% significance, it is just significantly different, all right? Sad versus neutral in blue-yellow. And when they looked at red-green, when we look at red-green, oops, no, it's not significant. At red-green, 0 is in the 95% confidence interval of this t-distribution, okay? So hopefully what you got doing it this way is that in the for blue-yellow, the t-test says they're significantly different. In red-green, it says they are significantly different. A little note here. So just to kind of point out what's happened here is that what's happened is that they've said that for blue-yellow, that's this dashed line, the difference between neutral, which is up here, and sad, which is down here, is significantly different. This is a significant difference between neutral and sad. Okay? For red-green, the difference between neutral, which is up here, and sad, which is down here, was not significantly different. The authors of this study then went on to conclude that there is an interaction, because for one of the color perceptions there's a significant difference and for the other there isn't. So they're saying that color perception based on an emotion, they interact in such a way that for one color perception there'll be a difference and for the other there won't be. All right? And they published that. It was only later, after they published it, that people said, hey, what's going on here? You're asking whether there's a difference essentially between this slope here and this slope down here, okay? But you've done it with 2 independent tests. Each test is not cognizant of what's going on the other test, okay? If you wanted to compare these 2, well, wouldn't you put all the information together in a singular test potentially? And that's what we can do with ANOVA, all right? So with ANOVA, we can actually put all of this together in a single test and ask, you know, here's our formula, our model, and I'll talk about models maybe in coming weeks. But here's our model, the accuracy, and this is across red, green, and blue, yellow. So what I've done is I've taken the blue, yellow data, the red, green data, I've bound them together, and I'm doing an overall test on the total accuracy of red, green, and blue, yellow, looking at the color axis, is it red, green, or blue, yellow, and looking at the emotion condition, is it sad or neutral, and then looking at the interaction of the color axis and the emotion condition. And what we see here is actually the interaction is not significance. It's very much not significance. The p-value is actually very large, nowhere close to less than 5%. It's like 62% or something, all right? So that's kind of interesting. When we do a joint test, when we test these things together to test for the interaction, the results are completely different than if we do 2 independent tests, okay? So this is one of the reasons, and I was kind of hinting at this in previous weeks, this is one of the reasons why we do something like an F-test instead of just doing a whole bunch of t-tests, right? Which is that when you put all this data together and all the information together, you often get a slightly different statistical story than if you just do everything separately and just do a whole bunch of independent tests, okay? So in this case, the conclusion that should have been made is that there's actually no interaction. Probably this paper should not have been published. But it goes to show a few things, and I'm kind of showing this I'm making this point for a few reasons. One is, statistics is hard, and it's not intuitive to those of us who are not trained classically in statistics, all right? So it's dangerous to make ad hoc decisions and just do kind of something that makes sense to yourself when you're playing with statistics. It really helps to have a statistician in the room. All right, it really helps to run what you're doing past somebody who's an actual statistician. They may not know anything about your domain, they may not have any concept of your theories, but they've spent their life understanding statistics. That's fine. And for many of us who are using statistics in like data analytics and experiments and whatever we're doing, we have to straddle this two worlds where we have to kind of have some domain expertise. Maybe we have to know something about psychology, I suppose, or color perception, and at the same time we have to understand statistics at the same time. We can't be masters of both, and typically for those of us who are data analysts, we are more often leaning towards the domain side. Okay, so when you are doing this kind of work, you need to get this reviewed by someone who has strong statistical chops. All right. So that's one thing I want to mention. Don't make ad hoc decisions on statistics just by what works intuitively to you. Statistics is not intuitive to those of us who don't have statistical training, all right? Like rigorous and extensive statistical training. I don't mean like just BACS, okay? All right, so that's one thing I want to just get out there, all right? Always get your stuff reviewed by somebody who may not understand the domain, but they can at least understand the statistics better than you can. All right, okay, cool, that's one thing. What happened? So this paper got published with those two t-tests, and then people started calling that study out. This was a blog article written by I believe a master's student at some university who read that article and said, hey, wait a minute, that doesn't work, and ran this ANOVA experiments. And he wrote this very scathing blog article on the importance of visualization. And we see that, right? When we visualize things, they're not as clear as the statistics might lead you to believe. The second part of the title is even more scathing, all right? So it wasn't just him. This student and several other people started blogging and tweeting about like, what's going on here? This article is this analysis doesn't make sense that got published. And sure enough, after a deeper review, the journal retracted the article. They actually withdrew the article. They unpublished the article and said, oops, we made a mistake. All right? But it's important to kind of look at this. They do say that, although I believe it is already clear, I would like to add an explicit statement that this retraction is entirely due to an honest mistake on the part of the authors. Okay, these authors were not trying to trick anybody. They made a mistake. All right. Okay, cool. When I saw this whole thing transpiring, I was like, I have to get my hands on this data set. This would make an excellent BACS assignment. But sadly, the journal had also removed the data from the journal website. Boo. So then I went to this guy and I was like, hey, I like your blog article. Do you happen to have the data that they actually used? And he wrote back to me and he said, yeah, I kept it. I mean, they removed it, but I kept it, and certainly you can use it for your class or whatever you want to use it for. Like, yes. So I was able to get a hold of this data for you to play with. All right. Okay. So anyway, I hope that drives home the point that save yourself some embarrassment, get your work properly appraised by people who are more adept at statistical concepts. Okay. In fact, in this case, it's not the author's fault at all, to if you ask me. I think it's the journal's fault. They should have picked reviewers who were capable of finding this kind of a little mistake and saying, hey, this is an elementary mistake, please don't do it this way, okay? Which is one of the reasons when I talk to PhD students particularly, I always emphasize that the quality of the journal you're sending your work to is vital. If you send your work to a flimsy journal, they will publish your flimsy ideas. It's better to send it to a place that, even if it doesn't publish, it tells you this is wrong, and you don't have to embarrass yourself later. All right. Anyway, so though this is embarrassing, I hope this is a good learning lesson for all of us, and the authors really made a genuine mistake. Okay. All right. Cool. I don't want to go over the whole homework in too much terrible detail. I do know there was a lot of questions about the statistical power part of the assignments, okay? In which, so let's, I mean, I'm not going to go through all the scenarios and everything. Sorry. All right. Go away. All right. So let's take a look at what's happening here. Can I make this a little bit wider? Yes, I can. Okay. So I gave you a bunch of scenarios where I asked you, here's a situation, what would happen? Okay. Now let me make something absolutely clear, because I think some of you will be nervous about, like, oh my God, did I do it correctly? The point of this question was not to get you to come up with the right answer. It was rather, the point of it was what transpired on the discussion boards was to get you to ask questions about what should happen here, what should not happen here, and to discuss with other people, like, what is this really all about, okay? So I do ask you, when you're doing your peer review, don't grade this question too harshly. I mean, not too harshly. If they're obviously completely wrong, that's one thing. But if people have written out their assumption and said, I think this will happen, and then that's why the diff or the SD or the N or the alpha will change, that's fine. You know, just look at if they try to justify what they think could have happened. Okay. But the point of the assignment was also to get you to think about how these different types of errors actually affect the results that you're getting. All right. We can do it by just staring at the formula and saying, oh, the numerator will change, the denominator will change, but it's boring. It's much more fun for me to look at a visualization and see change in real time as we are changing our assumptions, all right? So I love this manipulate function in R that allows you to kind of create a visualization so easily and then just slide these little things around and see what happens, all right? So no surprise that, you know, if you have a condition in which systematically everyone answers in one direction, it might change the diff, the actual difference that you're testing, right? And you will go from potentially having a non-significant answer to having a significant difference, or from having a significant difference to having an insignificant difference, okay? So either ways, you could have bias in either directions, all right? So I hope that much is clear. What's also important to note is that if the data you're collecting is not measured as precisely as possible, and there's a lot of variance creeping into your measurements, it affects your tests, right? So whatever phenomenon you're measuring, if you have more variance, can you see like what happens to that alternate distribution? Maybe not what you think would happen. Like intuitively, if I just showed you this picture earlier and said, hey, the variance is going to change. Let's pick a borderline case, okay? Borderline, there we go. And I was to tell you, hey, my measurements were not that precise. I think they were accurate in that the mean should be accurate, but like, you know, they're spread out a little bit more than I would have liked it to, okay? For example what? I want to know your weight for some reason, and I just ask you, what's your weight? And you just kind of tell me what it is, rather than me actually making you stand on a scale. Some of you may go under, some of you may go over, probably most of you will go under. But imagine for a moment you go and you're guessing your weight, and you're guessing in both directions. Some people are guessing too little, some people are guessing too much, right? Your standard deviation of your measurements is getting wider. And if you look at this picture, you might be tempted to think that if my measurements are getting wider, then these two distributions will get wider. But that's not actually what happens. These two distributions, like the alternate distribution, starts walking to the left. It just starts shifting to the left. Isn't that interesting? It's not exactly what you might think would have happened. Okay? The scale stays the same in the bottom. Whereas if you were to measure more precisely, that distribution starts walking to the right, and you're able to detect differences. All right? So this is kind of interesting. So I mean, you know that, right? Intuitively, at some degree, that if my measurements are highly precise, I can, find differences easily. But this is a visualization of it. Okay? Is that your alternative distribution actually starts walking to the left or the right depending on the standard deviation of your measurements. All right? So I hope that kind of gives you some sense of why the variance of your data produces type 1 or type 2 errors. All right? All right. And then the next thing, and the other thing I want you to kind of keep in note of is, so let's go back to this kind of a situation. Let's say it's just borderline or not significance. And the other thing to keep a note of is that sample size has an effect. But everyone knows this. I find that everyone nowadays knows that, yes, bigger data is better. We live in a big data world. And if the sample size increases, yes, that alternative distribution walks to the right again. All right. So that means a few things. It means, on the one hand, you must collect enough data, right, if you want to detect a difference. But this is a weird thing to say, because if you collect a lot of data, then you will find a statistical difference. And this is a bizarre thing to kind of wrap our heads around. So let's think about that again for a moment. If I don't collect enough data, I will not find a difference. But if I collect more and more data, I will find a difference. So, if I have an insignificant result, I could simply make it significant by collecting, I don't know, another 1,000 records, another 10,000 records. It will become significance. That's a weird thing, isn't it? It means that there's no such thing as too little or too much data. It's more like, do you want it to be significant or not? All right? And I hope that, and this is the second thing I was kind of doing, the thing I was hoping to get out of this homework, is I want you to realize that to a certain degree, no, not to a certain degree, to a great degree, significant results don't mean anything. It just means you had enough data to find a significant difference. That's all it means. If you don't find a significant result, you can just collect more data, it'll become significant. The difference will not change. Notice the difference is not changing. The difference is stuck to where it was in the beginning. I'm just changing n. And I can just make this rapidly change just with a few hundred data points. Nowadays, we do experiments or collect data with tens of thousands, hundreds of thousands, or millions of data points. You can make anything significant if you just collect enough data. All right? Does that bother you? Doesn't bother you? You're like, eh. It should bother you a lot. It should bother you a lot. Because what the hell is significance good for then? Right? Like if someone says, oh, there's no significant difference between this drug, and someone says, hey, let's just do it on another 10,000 people, it'll become significant. What? The drug didn't get more effective. It just became statistically significant, that's all. The difference didn't even change. All right? So we've known this forever. We've known this for like, I don't know, a century or more. And this, but it's, I mean, we're verbalizing this more in the recent years, in the past, I would say 10 years, particularly in the past 5 years, where people are saying this whole thing called significance doesn't make any sense. Why? Because I can make anything you want significance, right? Just make n bigger, all right? There's some nice ways that I think you can try to make things significant, like for example, oops, excuse me, not alpha. For example, you know, getting more accurate measurements, okay? But there's a you know, limit to how much accuracy you can possibly get out of your measurements, okay? But that's a good way to make things significant. But there's no upper bound to how big your sample size can be, and that's a problem. All right. So results are not significant. Keep collecting data; it'll become significant. Which means that significance doesn't really mean anything. All right, because you can make anything significant with enough data. So what the hell do we do with this thing called significance? Like, does it mean anything? Like, does it actually mean that there is a difference? No, not necessarily at all. All right. I guess the way I would like you to think about significance is perhaps the following. All right. Perhaps think about it like you're investigating an object. All right. If I hold a tennis ball right up to your face, this is a tennis ball, by the way. If I hold a tennis ball right up to your face, right? This is right up to your face. You cannot see, you can smell. Can you smell it? You can almost smell it, right? If you play tennis, you can smell this picture. You're like, I know that smell. It looks very different than if I held it very far away from you, like this one right here, right? If I hold the tennis ball very far away from you, how would you describe this object you're seeing right here? Could somebody describe this object? A circle? Anything else? Yellow. A circle, maybe a sphere. You don't know it's a sphere, it's far away. But it's round. A yellow round object. Is it a very round object or a kind of round object? It's a very round object, right? But then I bring it a little bit closer to you. This picture, depending on how good your eyes are, do you notice anything different now? What is that? You're seeing some white lines in there. Okay, so it's still a round object that's yellow, but it's got a couple of white lines in there. Fine. Okay. What about this object? Do you notice anything different now? Let me ask you this. The texture, would you still call this a perfectly round shape? No? No? Why not? Oh, okay, so yes. Yes. These are not just two white lines running through the ball, they're actually two ridges, or not ridges, ditches. The opposite of a ridge, a ditch. Two ditches running through the ball. They're quite deep actually. And if you notice, like in this area, the ball is not quite round here. It just kind of like stops being round and then starts being round again. Right? So now you would not call this perfectly round anymore, apparently. And it's not smooth. Well, you notice that in this last image, right? This is not a smooth object at all. So, were you completely wrong when you saw this picture and said that it's a round ball? Were you wrong? You weren't right. Thank you. Well, how about this? And I'm surprised no one's saying it because it's the favorite answer of students everywhere. It depends on what you're trying to do, right? If you're trying to play tennis, I could start playing tennis with this ball, right? That's the second image right here. Yep, looks like a tennis ball, let's get playing. All right, I'm happy. If you just want me to identify round objects, I'm pretty happy with this image right here. It's round, good to go, right? Now, if you want to make sure that this tennis ball is actually follows the rules and regulations of like tennis associations, is a legal ball for competitive use, then maybe I need this picture here to make sure what? Actually, there's some rules in tennis about how thick the yellow parts can be. Like it can't be super thick. There's a regulation. So maybe from this picture, I can start saying, yep, it looks like a tennis ball. I can kind of measure its dimensions if you give me a scale. And the ridges look to be about regulation. So yes, this is valid for official tennis play, not just hobby tennis play. This is now an official competitive tennis ball. But if you don't know, when you go to buy tennis balls, you can buy competition like regulation tennis balls, or you can buy what we call practice tennis balls. Practice tennis balls don't have all the properties of a official tennis ball, but it's good enough just to hit the damn thing back and forth and have some fun. Okay. However, imagine I was using this object to not play tennis, but I needed a very, very smooth object, a soft and smooth object to polish a high-power mirror on a high-power telescope, like some kind of astronomical device. Okay. Then maybe when I zoom in on it, I'm like, hey, this is not smooth at all. I need it much smoother than this. You're gonna scratch my mirror. So the question is really, what do you need it for? So I think the better way to think about significance is really about how significant is it relates more to what do you need it for. All right. So do you just need to see, is there a difference? Do you need to see if there's a difference so that people will, be entertained by it or they will buy it? Do you need to see that there's a difference that produces like clinical changes, like it is actually measurably changing a human being in some way, like a drug is actually changing certain hormone levels or something in your body? Do you need it to cure a pandemic? I don't know, So depending on how scientifically rigorous you need to be, how important the need is, how much significance you need is really up to you. Okay? So actually the significance is not as important, I would say, as perhaps the difference, right? Look at the difference. Is the difference big? Okay, is the difference useful for what you are trying to do? That's another thing. The significance you can use still, the p-value and your significance, you can still say this is significance, but maybe 5% significance is good enough to have a casual conversation about something. Or maybe even have a scientific discussion about something that is not terribly critical. All right? But if you're trying to do an experiment that will change what you think are the laws of the universe, maybe you need a lot more significance than just 5% significance. Okay? And that's actually the way scientists really do it. If you're publishing in physics and high energy physics, alpha 5% doesn't cut it. You're going to need something like, I don't know, 0.000, several zeros and then a 1. All right? So don't take significance to literally mean it is and it is not difference. Use significance, calibrate it to how important the task you're trying to do. How important is it to be right in this situation? All right? And how right do you want to be? There's a lot of comments coming out from the scientific community. This was one of the other optional readings I put on Canvas. Read it. It's very readable. It's a comment in the journal Nature, which is one of the most eminent scientific journals out there, where they really had this article that said it's time to retire this idea of statistical significance. It's maybe time to put it to bed. All right? But actually they don't say exactly that. You read it to see what they say. So researchers have been warned that a statistically non-significant result does not prove the null hypothesis. Every statistical student knows this now. If something is not significant, you haven't proved the null hypothesis, right? And we also tell students if something's statistically significant, it doesn't prove the alternative hypothesis. It just gives you some more credibility to it, okay? But it's time to go beyond that. It's time to tell students, or not students, researchers, that we may have to just abandon this notion of statistical significance, all right? It is possible with even fairly high power for two people to conduct the same experiments, one person to get a tiny p-value, the other person to get a very large p-value. It's actually surprisingly possible, all right? But they're not saying but at least these authors are not saying ban p-values. They're just saying don't use significance and p-values to make a yes or no decision. It's not about, yes, this is true, publish. No, this is not true. We can't get published. Okay, and that's part of the problem that's happening in scientific research. There's so much pressure on researchers to publish that they're doing whatever they can to get significant results. All right, and if they get non-significant results, they're not publishing those. That's another problem. So everything you read in science is biased towards things that are significant. All right, and as a result, when you try to replicate studies, we get completely nonsensical results. For example, if someone runs an experiment and they are that lucky 1% that finds a significant effect where they shouldn't be, they're going to publish it. If you try to replicate it, you're not going to get the same results. So we have a bias towards significant results in scientific literature. All right. So they're just saying don't treat p-values categorically, yes or no. They offer another suggestion that I'm not going to go into. They say, first of all, stop calling it confidence intervals because it has nothing to do with the confidence of your findings. And they suggest the term compatibility interval. And they say, look at the whole interval when you have a result. Look at the average value of your, let's say if it's a t-test, look at the average, you look at your t-value and ask, is this good enough for what we're trying to do? But then, look at the two ends of the confidence interval and ask yourself, at the low end, would this still be useful for us? At the high end, does this have any other meaning that is important to us, okay? So I won't go into this more right now, but just to kind of put it on your radar right now that the scientific establishment is increasingly frowning upon people just finding things significant and saying, yes, significant, let's move on, okay? And I think, do I not have this here? Well, we'll talk about it later, okay? One of the things they really encourage is that we should embrace the uncertainty in our data, and we shouldn't just think of our data as giving us a categorical response, okay? All right, so that's that, all right? So that really does conclude what I wanted to say about hypothesis testing, all right? And I hope you've gotten a fairly stronger understanding of it than potentially you had before. You understand now it's not just a simple yes or no test. There's many interesting things going on. And you understand the value of each of these null and alternative distributions and the information you can extract from both of them together, okay? And don't overly rely on significance. It's just one more toolkit in your explanation, right? Great. Any questions on this? You're okay with it? Whew. All right. Okay. All right. So thank you for getting that homework done, and I hope this kind of reinforces our lecture today, reinforces the findings of that homework as well. All right. Good. Let's just take a little 1 minute stretch break. Homework behind us. Forget it ever happened. Erase that part of your memory. All right. Stretch out, relax. We're no longer talking about the homework. Instead, we're going to start talking about the next homework. No, I was kidding. Like, this nightmare. All right. All right. I want to do something which is fun for me, maybe not for you. I want to go back. I mean, that's why I'm teaching the class, for fun for me, right? Work for you. I want to go back to a question I asked you in the first week of class. Do you remember who you were in the first week of class? You were so naive, so innocent. Wet behind the ears, we say in English. Do you know what that means? Wet behind the ears? What do you think that means? It's like, children, when they come out of the shower or out of the bath, they don't really know how to use the towel super well, and they're still wet here and there. So wet behind the ears means you're still innocent. Still haven't dried yourself. Okay, I want to ask a question way back, before we even learned anything about anything. When you first started learning how to code in R, right? And the very first lesson in your swirl tutorial, I asked you why, I think I can kill this now. I asked you why do we call that a vector? All right? We said that's a vector. And you faithfully said, yes, that's a vector. And I asked you, why the hell is that called a vector? Like, why do we even describe these numbers as a vector? Like, what could it possibly, what advantage could we possibly have with this kind of expression? Why not just call it an array like other programming languages do? Like, it's an array. Or a list or something. Like, why do we insist on calling these things vectors? And every year I ask students, why do you call this a vector? And in fact, it was in your first or second assignment. I think it was in your first homework assignments. There was an optional question, or maybe it was ungraded. It was an optional question asking, why do we call this a vector? Why do you think we call this a vector? All right. And these are some responses from over the years, one or more maybe from this year, but these are a few representative answers from over the years of students taking this class. And some student says a vector implies it should have a direction in a dimension or even in n-dimensional space. Dun dun. All right. And using a vector, we can do some linear algebraic operations. Somebody who's done linear algebra. Fine, fantastic. Somebody else said, R was born for statistical computing. In math, we calculate vector or metric operations. A vector structure is more beneficial. That's why it's a vector. It's a little circular explanation there. It's a vector because vectors are helpful. That's why it's called a vector. Got it. I like this one. Vector feels like a series of values with direction. So C 1, 2, 3 and C 3, 2, 1 are actually different. Interesting, intriguing. By the way, what is a vector? Like, do anybody remember it from your geometry class in high school? By the way, in Taiwan, do you study geometry in high school? Yes? Yes, right? Everyone does. I hope, I think, I don't know. What is a vector again? Does anyone remember the definition? Not really? Oh yes, please, sir. We have an engineer here.
So usually that has magnitude as well as direction.
Yes, just exactly as your teacher told you. Yes, you memorized it. You're like, must pass this exam. And yeah, okay. And little did you know that years later you'll be asked again. So your teacher did well. It's what did you call it? A unit, or what did you call it?
Yes, I guess it's
A unit. Okay, or something. It's something that has magnitude and direction. Wow. All right. So it has magnitude and direction. So essentially, let's take a look at this. So this is a vector. It has what we call a magnitude and a direction. What do these things possibly mean? Let's try to visualize this vector. But before we do, I want to introduce you to some other code. This vector that you're seeing in R is technically called a column vector. Okay, I'm going to get in a moment to why it's called a column vector. And technically in math, it should be written like this. It should be written like the 4 and then the 2 below it. It should be written as a column, like straight up and down. It's a column vector, all right? So that's actually, if you remember little vectors in linear algebra or math, that's a vector, all right? And it's got this little arrow on top of it to let you know it's a vector. Okay, it's wearing a little hat, okay? A row vector would have would be written like this. It would be written left to right. Unfortunately, in our editor, we cannot write up and down, so we write a column vector like this, but it should be really written up and down, okay? If I take the transpose of the vector, which means, transpose means you flip the rows and the columns around, you just rotate the thing, all right? Then, yes, R will say, yes, this is a column vector. This is now this is a row vector, and it will write it as a row in a matrix, all right? So this is a little matrix with one row and two columns. Interesting, okay? So that's vectors, all right? Let me quickly visualize this vector. And in R, if you want to visualize it, and if you want to treat the first value as X and the second value as Y, you need to actually transpose it and make it a row vector first, okay? And let me just plot what this is. Oh, that's all I get. I get a point out here at 4, 2. All right. R is not really plotting the vector, it's just plotting the point at 4, 2. If I want to make this look like a vector like you learned in school, I have to draw an arrow. So the arrows command is just like the segments command. You tell it the starting X and Y and the end X and Y. So starting from 0, 0 to the V, to the vector V, first component, second component, all right? And let me draw this arrow, bang, that's a vector, all right? It's a vector because it's got a direction, first of all. It's pointing in which direction? That direction. It's pointing in, this is literally an arrow pointing in that direction. So it's two numbers which have a direction, all right? And it's pointing in that direction. What's this whole magnitude thing about? So magnitude means it has a size, all right? I could have many vectors in this direction, right? I could have a vector from, I could have a vector from 0, 0 to, all the way to 2, 1. It would be in the same direction, right? If I had a vector that went from 0 to 2, 1, that's about here. It's in the same direction as this vector, but it would have a different magnitude. It would have a different length, right? Anybody remember how to compute the magnitude or length of a vector? Yes? No? Kind of? Sort of? Anybody want to take a guess? Yeah? No? Okay, moving on. We'll see it in a moment anyway, okay? I'm not going to let you get away with it that easily. But before we talk about that, let's, other things you can do with vectors, you can multiply them, right? So we can multiply our V vector 4, 2 by 3, and this multiplies every component in that vector, okay? Will this vector change direction if I multiply it by a number? Yes or no? No? Think about it this way. Imagine I multiplied this vector 4, 2 by half. What would the new vector be? If I multiplied V by a half, what would 4, 2 become? 2, 1? Yeah, 2, 1. Has it changed direction? 2, 1? Nope. So multiplying a vector by a scalar does not change its direction. Okay, good. We're getting somewhere. What if I add, can I add vectors together? Sure, we can. This is now 8, 4. Okay. This has not changed direction solely because both vectors V and V are going in the same direction. So it has not changed its direction. Otherwise, it would change direction. Okay. So some basic things about vectors. So what's so great about vectors? To help you understand why people in the world of analytics are obsessed about vectors, to give you a very simple explanation of why they're, it's not simple, it's going to take me 1 hour. It's going to take me like most of the rest of the class. To give you an explanation of why we call these vectors and why vectors are interesting to us, I want to look at a semi-fictional case study of data, okay? It's semi-fictional because the data is, well, potentially real. The data for today is going to be fictional. I'll give you the actual data for your homework, however, okay? The story is actually real, and it's about a company. The company is called Cardinal Blue, and they make an app called Picolage. Anybody use this app? Anybody has this app or use this app? Anybody? Nobody? Okay, interesting. Usually there's some students in the class who have this app. Maybe the folks watching from home are like, me, professor, me. But too late. It's actually a very popular app. Several years ago when I was kind of collaborating and talking with this company, their app was in the top 10, I think, of the Apple App Store's media section. Number 1 was YouTube. Maybe number 2 was Instagram. But this was the top 10. That's freaking good. And this is from a company in Taiwan. Okay? And it's great. It's an excellent company. It's an amazing startup. And I don't know how many people they have now, but probably I'm guessing somewhere between 50 and 100 people. I don't know. So it's not a very large company. It's a very small company. And at that time, that was many, many years ago. That was maybe like 5 years ago almost. At that time alone, they had like about 100 million downloads of this app. So it was a fairly heavily used app. And they had like tens of millions of active users every month. Okay. And what this company was doing is they basically, they have an app that allows you to take photos that you've taken and put them together in a larger picture. Okay, so imagine you've got some photos of your friends. You can just kind of put them together in this picture with a background, and you can write some words on it, right? It's called a collage. And interestingly, you can add stickers. Like, you know, online how you have stickers that you can buy and add. You can buy stickers from their store, and you can just kind of add it to your collage. All right, and selling stickers is how they make their money, at least at that time. They essentially, the app is, I think, pretty much free, but if you pay for the app, one thing is that there's a little watermark in the bottom saying created with Picolage, and that's removed. And if you and you can buy stickers. Okay, so actually you don't have to buy I don't know if you have to buy the app, or you can just buy stickers, and those stickers will remove that watermark, I think. So and that kind of allows you to kind of create these little friendly pictures. You can buy a heart-shaped sticker, little flower, some glasses to put on your friends, some silly things like this. Okay. So imagine they want. A couple more details. They have a sticker shop, so in the app you can actually go to the sticker store, okay, and you can buy stickers here. So for example, here's some stickers for spring break, succulent garden, spring rose, etc. And they have some price. Some are free, some are pay money. And notice you don't buy a single sticker. You have to buy a bundle of stickers. Bundle means a collection of stickers, okay? So Between Spring has all these different stickers that come with it. All right. And imagine now that they want to do something like the following. And this is a simplistic example. This is not how they do it today, probably. But imagine somebody is looking at a bundle of stickers like this one. It's called Birthday Fun. And it's these stickers. Okay. The company would like to recommend to that person some other sticker bundles that they might be interested in buying. All right? The question is, how do you do this? One thing is, and when I met the company at that time, the way they were doing it is every time they designed a new sticker bundle, the designers, the artists, would look at all the previous sticker bundles and say, oh, I think some other good ones that go along with this are this, and this. Okay? So they were doing it by hand. And at that time, I think there were hundreds of sticker bundles. It was getting a little bit out of control. Like for an artist to reflect back on the hundreds of sticker bundles. Maybe by now, I don't know, it might be in the thousands. At some point, you've got to automate this. You can't have artists every time picking sticker bundles. Especially because the sticker bundles change, right? Like you'll get new ones. You want to always recommend these ones for this one? Maybe there's some new ones you want to recommend, right? So imagine they'd like to automate this, all right? And basically, we would like to create a recommendation system, essentially, where given a single sticker bundle, like birthday fun, we would like to recommend other sticker bundles to you. All right? There's several ways of going about doing this. I'll just discuss maybe one of the simplest ways of doing this, okay? And yet, one of the most heavily used. So, let's imagine our data looks like this. This is a small subset of the data. They have, let's say, hundreds or thousands of bundles, but I'm only showing you 4 bundles on the screen right now. Bundle 1, 2, 3, and 4. All right? And they have, 100 million downloads of tens of millions of users every month, at least, But I'm only showing you 3 different user accounts. Account 1, account 2, account 3. Okay? The numbers in these cells are telling you how many times this user account has used this bundle. Okay? So, for example, whoever account 1 is, on their phone, they have used sticker bundle number 1 once, they've used sticker bundle 2 twice. They seem to be big fans of sticker bundle number 3 and a little bit of sticker bundle number 4. Okay? Account 2 is a heavy user of bundle 1 and bundle 3. They've never actually even used bundle 4. Never. All right? And account 3, they're mildly using some of the bundles. They've never used bundles 4 at all. Okay? What we'd like to do is understand. Now what we want to do ultimately is, given one bundle, let's say bundle 1, I would like to know which of these other bundles might I recommend. If you like bundle 1, which of these other bundles might you like? Does this question sound familiar? It's like when you log into Netflix and you're like, because you watched, I don't know, Narcos, you should also watch da-da-da, right? So because you like this, you should also like that, potentially. Again, there's many ways of making this recommendation. The way I would like us to think about it for the purpose of this class is, we want to find out which of these bundles are very similar to one another and which are not very similar to one another based on this data. Based on this data, or data like this. It might be bigger than this, might be a lot bigger than this. In fact, the data set I'll give you for your homework, I think it's going to be several hundred bundles, columns, and I think roughly 10,000 users. So it's going to be a very big data set compared to what we have seen before. Okay? But let's just take this little baby example right here. And my question to you is, how could we figure out which of, let's say given bundle 1, which of these other bundles is similar to bundle 1? Any suggestions? What's that you said?
3.
Oh, 3. Oh, we have an oracle here. Okay. 3. Interesting. You think bundle 3 is similar to bundle 1. Why? Because?
They're similar in account to account 3.
Oh, because the way account 1 and account, account?
2 and 3.
Okay, account 2 and account 3. Oh, I see. Because account 2 and account 3, that's, they seem to like bundle 1 a lot, and they also like bundle 3 a lot. They're so-so about bundle 1. Account 3 is so-so about bundle 1, and they're also so-so about bundle 3. So it seems to be that potentially the people who like bundle 1 like bundle 3. The people who are not so crazy about bundle 1 are also not so crazy about bundle 3. Except, of course, for account 1. We should just delete account 1. Okay, you are banned from this app. You're ruining our calculations. Okay, so you're doing it visually, right? I mean, well, you're doing it observationally, actually, just observing the data in there. All right. Any other suggestions of how we could do this? All right. No? Okay. All right. Let's use vectors, because that's what we're here to do today. Okay. But before we do, let's take a short break. I know it's already a little early, but I think it's I want to get your energy back. So let's just take a quick break, and we'll come back and we'll discuss how to kind of approach this problem more quantitatively. We can't have Guild all the time staring at all the bundles and giving us answers, right? He's too expensive.